Hi class, today the video is about the derivatives of composite functions, which we also call the chain rule. So we actually did learn about the chain rule when I taught you about the product rule a couple of notes ago, but today we're going to go more in depth and get a bit more difficult with what the chain rule actually is, and like I said, some more difficult examples. So first we need to remember what a composite function is. And then once we can define and understand that, we can probably have some more understanding of the chain rule. So we did learn about composite functions at the very end of advanced functions. So it looks like an O there. It's not. That's just a small dot, an open dot. So recall that given two functions, f and g, then the composite function f composed of g is defined by f at g at x. So order does matter here. F composed of g means f at g of x. G composed of f would be g at f at x. There is a difference, which we'll show in the example. So to solve things like this, you can first find the value of g at x, and then that output becomes the input into f at x, as long as that output is in the domain of f at x. So hopefully this short example will help you reflect on the process of composition and remind you what's going on here. So if our function f is just root x and our function g is x plus 4, then what does it mean to find f at g at 12? Well, the first thing we would do is find g at 12. So that's putting 12 into this function, which gives us 16. So then we want to find f at 16 because g at 12 is 16. So now f at 16 is equal to root 16. So that is 4. Okay, now what if we wanted to go the other way, g at f at 12? Well, f at 12, that's putting it into this function, just gives us root 12. Okay, and so then g at f at 12, so g at root 12 gives us, we put in root 12 here, root 12 plus 4. Okay, and if we wanted to be really fancy, we could call this 2 root 3 plus 4. Okay, so that's how it works with numbers. So let's think about how it works with just variables. So f at g at x means that you're putting g at x, so x plus 4, in for f. So this is, think about this as f at x plus 4. So that would give you the square root of x plus 4. Okay, we've taken g at x and put it inside of f at x. But what if we wanted to go the other way? So g at f at x, so that's taking g at root x. So now we're taking root x and putting it inside to g at x. So that would give us root x and then plus 4 on the outside. Okay, it's really important you understand this process of composition, you understand that example. If you don't, please try watching this again or put a big asterisk next to it. Make sure you get those clarifications that you need in order to successfully understand the subsequent work. So if you have a composite function, then how can you differentiate it? Well, often we could expand it and just use rules we already have, but that is often time consuming and can be very difficult to do correctly. So the chain rule was created in order to make your life easier, I promise. It's not here to make your life harder. It is intended to make your life easier. So if you have f at g at x, then the function is you take the derivative of the outer function with respect to the inner function, and then multiply it by the derivative of what's inside. So this is something you've seen before, okay? So like if I did just quickly on the side, this means if I have like f at x is equal to bracket x squared plus 1 all to the power 4. So this means you would think about x squared plus 1 on the inside as g at x. Okay, so I would take the derivative of this. So I would treat this just like it's blah, like it's nothing. So f prime, so I take down the 4 like I normally would, okay, leave the inside and bring this down as a 3. So this part here is equivalent to what this is saying here. But then you have to multiply it by the derivative of g at x, so g prime at x. So that would be just 2x. So this part here is equivalent to saying g prime at x. So you're just taking the derivative of the outer function and multiplying it by the derivative of the inside function. So that's kind of the standard notation, but Leibniz notation is actually very useful with the chain rule. You're not going to believe me at first. You're going to say, Mrs. Weens, this is way too confusing. Believe me, if you are taking calculus next year, you will be learning related rates. You will need to understand this notation. Okay, so think about if y is a function of u, and then u is a function of x. So that would be like, for instance, if we have y equals u to the power 5, okay, and u equals 3x minus 2. Okay, so we have y as a function of u, and u is a function of x. Well, what if we wanted to take the derivative of y with respect to the change in x? So we want to so we know that u is a function, sorry, y is a function of u, but u is a function of x. So we are able to actually find the derivative of y with respect to x. So one way would just be rewriting this function and putting 3x minus 2 all to the power of 5. But another way of thinking about it is that we can just take the derivative of y with respect to the change in u and then multiply it by the change in u with respect to the change in x. So this is another way of writing the chain rule. So you take the derivative of this and multiply it by the derivative of this. So then y dy dx would be equal to 5u to the 4. Okay, so I took the derivative of y, but left u there with respect to u. And then I multiply that by the derivative of u, which is this function, with respect to x, which gives me just 3. Okay, and so now if I want it all in terms of x, I can just plug in this 3x minus 2 here. And you have the derivative. Okay, so this is just a way, I just did this little example to help you understand this notation, okay? One other thing to notice is that it makes sense that this reduces to dy dx because these du's would just cancel out, giving you dy dx. Okay, there is another example of that coming up, just so you know. Another way of understanding the chain rule is, for example, if you have y equals bracket some inner function to the power n, then taking the derivative of that, so y prime would be, you take down the n, you leave the inner function the same, you subtract the exponent here by 1, but then multiply that all by inner prime, so the derivative of that inner function. Or, for example, if you have y equals some big long square root of some inner function, so you're taking the square root of something, then the derivative of that would be, you would take down the 1/2, keep the inner the same, make this negative 1/2, but then multiply by the derivative of the inner function. So that's another way of thinking about it. So let's do an example, and then I'll kind of explain this further. So the derivative of here, so one way to do this first is to rewrite this, if you prefer, as 4x cubed minus 5 all to the 1/2. You don't need to do that step. It's just if you personally, if it helps you in differentiating. So we take down the 1/2, we leave the inside the same, we reduce the exponent by 1, and then we multiply by the derivative of that inner function. So 12x squared minus 0, so just 12x squared. So then now we can simplify this. So we get 6x squared divided by root 4x cubed minus 5. And that's it. That is a simplified version. Okay. So another way of thinking about this chain rule, and again, this is kind of in Leibniz notation, is as follows here. So u to the power, so if y is a function, if y is a function of x through the intermediate variable u, then the rate of change of y with respect to x, so let me write this as I go, then the rate of change of y with respect to x, that's what this notation means, is equal to the product of the rate of change of y with respect to u, and it's a product, the rate of change of u with respect to x. Okay, so let's actually fill this in. So if I were to take this as a derivative, it would be 3u squared minus 2. Okay, now if I were to take this as a derivative, I get 1/2 times 2, so 1, and then x to the negative 1/2 times 1. So this gives me 1 over root x. As this derivative. Okay, so if you need to actually go and figure out why this is true, you can do that on the side, but this is the derivative of that. So I have two choices now. Either I can sub in 2 root x here for u, or I can just find the derivative at x equals 4 by finding what u is equal to at x equals 4. So at x equals 4, u is equal to 2 times root 4. So 2 times 2, which is just 4. So notice that x is equal to 4 and u is equal to 4. That's actually just a coincidence. They're not always equal to the same thing. So here I would get 3 times 4 squared minus 2 all times 1 over root 4. So when you do those calculations, you get 23. Okay, so that is the derivative. All right, so that's kind of the basics of the chain rule. From now on, it's going to get a bit more complicated. So if you need to take a break, do that now, because now we're going to move on. So now I'm going to differentiate this h at x function, which looks super fun, doesn't it? So you have to think to yourself, is this first and foremost a chain rule question or a product rule question? Okay, and the answer that this is actually first and foremost a product rule question. So you should really think about this as y equals a times b. Okay, and you know how to differentiate functions that are products, a times b, right? You take a prime times normal b plus plus normal a times b prime. It's just that when you go to do those primes, when you go to do those derivatives, you'll have to incorporate the chain rule because each of these functions happens to be a composite function. Bummer, I know. Okay, but it is an important way to start thinking. Now, is this primarily product rule and then chain rule within that, or is it a chain rule that then I use product rule within? Okay, so this is, think about this as one function times another function. Okay, so we're going to leave our first function the same as our first step. So that's our first function. But now we have to multiply it by the derivative of this second function. So I'll use a different color just to show. So the derivative of the second function is you bring down this 3, you leave the inside the same, you reduce this exponent by 1 to get 2, and then you multiply it by the derivative of this inside function. That's the step that people forget. Okay? And so now That's 1 times the derivative of the other. And now we have to add, taking the derivative of this first guy. So you get 4x squared plus 3 to the power 3. And then times 2x, because that's the derivative of this inside. And then you multiply it by just the original of the other function. Doesn't this look super fun? Okay, I'm going to default to one color now. So now that is actually the raw derivative. That is the derivative. It's just that we can do a lot more simplifying. Okay, so let's just kind of do this in stages. So notice here that we can put the constants together. So 3 times 4 is 12. And then these are not common, so we'll leave them the way they are. So x squared plus 3 to the power 4 and 4x minus 5 all squared. Plus, okay, now we have 4 and 2x, so that's 8x. And then x squared plus 3 to the power 3 and 4x minus 5 to the power 3. Okay, so now you might be thinking you're done, but now we can actually common factor. Okay, so when we're common factoring, look at this in 3 different sections. Okay, I have this section, which is kind of my stuff on the outside. Then I have this section, which is my x squared plus 3's. And then I have, I don't know, how do I differentiate this? This section, which is my 4x minus 5's. So I can create 3 different common factors in a nice big square bracket. So what's common here is 4. So I can common factor out of 4. Then if you look at my x squared plus 3, I can take out a common factor of x squared plus 3 to the power 3, because each part contains at least 3 of them. And then I can take out 2 4x minus 5's. Okay, so that's what I've common factored out. So now I need to multiply that by what's left. So in this part, what's left to get from 4 to 12 is 3. And to get from x squared plus 3 to the power 3 to the power 4 means I need another x squared plus 3. And then I'm done because I already have that. Now I need to add bracket a 2x to get from 4 to 8x. I don't need to add any x squared plus 3's, but I do need 1 4x minus 5. Okay, and now this part can be simplified, okay? So we get this common factor here. Okay, and then when you expand and simplify what is in this second square bracket, you get 11x squared minus 10x plus 9. And there you go. So that is a simplified version of this derivative, okay? So again, this first line in the green, that is the derivative. I found the derivative already. The purple lines are the simplification, which again is required for you to understand as well. Okay, now we get a word problem, which I'm hoping will help deepen your understanding of the chain rule. So in this situation, we have the daily levels of carbon monoxide in a town, okay? So it makes sense that the more people that there are, the more carbon monoxide there is. But not only that, they're saying that the part per million actually increases per person or per 1,000 of people. So it's not that it just is a linear thing. So what this example is saying, it has 2 different functions. So it has the carbon monoxide, the C at P. So that's the parts per million in terms of the population in thousands. So this function would give us the information about, you know, if there's 10,000 people in this city, I would put in 10, and that would tell me how many parts per million of carbon monoxide there is at 10,000 people. If the population was 200,000 people, I would put in 200, and this would tell me the parts per million at 200,000 people. Okay, now think about the derivative of this. If I found the derivative of just C at P, that would tell me how carbon monoxide is changing with respect to the population. So as population changes, how does the carbon monoxide change? However, population itself can be modeled as a function of time. So they found that the population is changing with respect to time in this way. It's a quadratic function. And that's how it's increasing, where population is, again, in thousands. So they want to know, if I found the derivative of just this function, that would tell me how is population changing with respect to time. Okay, at what rate is population with respect to time? But this question wants to find how is carbon monoxide changing with respect to time. So I actually need to take that population function, make it with respect to time, and insert that into the carbon monoxide function in order to achieve that. Okay, visually, this is the C at P function. So this description, this picture, assumes that we have our carbon monoxide in parts per million as this axis, and that this axis is the population in thousands. So you can see that it is increasing rather steadily. Okay, now this function is population with respect to time. So now population is on this axis and time is on this axis. But we want a new function. We want C at P at T. So that's what this red function is. This red function would have carbon monoxide here, and it would have a time on the bottom. And you can see what the function actually turns out to be. So they take this P of T and they compose it. They put it inside this other function. So when we're taking the derivative, we have two options, okay? One is to use Leibniz notation, which is what I'm going to show you. And the other is to rewrite C at P as a composite of T and then just take that derivative. So I'm sure this talk is kind of going over your head right now. It's a lot of technical talk. So let me go through this. So we want to find dC at dt at t equals 3. That's what we want, okay? We want carbon monoxide changing with respect to time. So that's C over T. So based on what we know that dC of dt is going to be equal to dC with respect to P times the change in P with respect to the change in time. Okay, this is the chain rule. So we're actually able to find that now by taking these derivatives. So the derivative of C with respect to P, okay, I would take down the 1/2, leave the inside the same, and leaving P as the variable. And then take the -1/2 and multiply it by the derivative of this, which is actually just P. So that is my dC dP. Okay, now I'm going to multiply that by dP dt, so the derivative of this guy. So the derivative of that guy is actually just 0.2 t. Okay, so now to actually solve this, I know that I want my t to be equal to 3, but what do I want my p to be equal to? Well, to find what I want my p to be equal to, I find p at 3, since I want my t to be 3. And that, it turns out, is just 4, okay? Because it's just 3.1 plus 3 squared is 9, so plus 0.9, so you get 4. Okay, so now I just sub those in. So I let t be equal to 3, and I let p be equal to 4. And when I sub that all in, I get 1/2 0.5 times 4 squared plus 17 to the negative, that's a decimal by the way, to the -1/2 times 4, and then 0.2 times 3. Okay, so you don't need to simplify it in a word problem because all we actually care about is the actual number. The question didn't ask for a function. If the question wanted the function, then it would be important to simplify it unless it said not to. But this question wants just a number, so there's not really any point in wasting our time in simplifying it. So here we go. We get 0.24 ppm per year. So what does this mean? It means that carbon monoxide is increasing. Okay, that's why it's positive. So it's increasing at 0.24 parts per million per year, 3 years from now. Okay, I said there was another way of solving this. I'm just going to show it kind of above because I ran out of room here. So the other way of doing this is to rewrite C as a function of t. So C at P at t, it would be equal to really long square root 0.5. Now instead of this P, I'm going to write this 3.1 plus 0.1 t squared in there. Okay, and then that's squared plus 17. So if you like this better, you can rewrite the function this way. Now it's all in terms of t, and now you just find that derivative. Okay, and then sub in t equals 3, and you should get the same answer. Okay, this next question is not a word problem at all. It's just a difficult chain rule question with a lot of steps to kind of show another technique that you'll need when you're solving derivatives for big things like this. So remember, derivative is just rate of change, just the slope of the tangent. Sometimes we forget that. Okay, now again, first and foremost, you can see that there's a quotient, and you can see that there's a chain rule because we have a big function inside of something to the power 10. So is this first and foremost a quotient rule problem that we'll have to use the chain rule in, or is it a chain rule problem that we'll have to use the quotient rule in? So in this case, it's first and foremost a chain rule question. Just think about this as blah to the power 10. And when we get to having to take the derivative of blah, that's where we think about the quotient rule. So this is just something to the power of 10. So when you have something to the power of 10, you bring the 10 down, you rewrite that something, and that's now to the power 9. But the problem is that now I have to multiply that by the derivative of that something. So now it's just the quotient rule. So it's the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. And you're like, please, Mrs. Williams, let that be it. Nope, we're going to simplify this because we can. So careful, that's to the power 9, not a multiple of 9. Just be careful there. So we can leave this first part the same for now. But we can simplify what's going on in here. So in here, what you get when you simplify this whole numerator, you get 4x. Okay, oh, sorry, that should be squared. I am trusting at this point that you can do that, okay, that you can simplify that numerator to 4x and that you've had enough practice with the quotient rule to do that. So now the question is, can we do more? Well, yes, we can always do more. Notice that these denominators are the same. So just to confuse you less, I'm going to write this as 3. So 10, so you can think about it as 10 over 1, times 1 plus x squared to the 9 divided by 1 minus x squared to the 9, okay, because that 9 goes to both the top and the bottom, times 4x over 1 minus x squared squared. Okay, so now I just want to put all the numerators together. So I get 40x, okay, 10 times 4x, times 1 plus x squared to the 9. But on the bottom, because these denominators are the same, I can add the exponents, and I have 1 minus x squared to the power 11. So that is the simplified version of the derivative of that crazy function. Okay, I know you're hungry for one more. Just got one more. Look at this guy. This is so fun. You get in the groove and you do these, and it's just, you'll never have more fun in your life. So this is first and foremost a chain rule question, and then there's a whole bunch of other stuff going on the inside. But the fun of this is just being able to unwrap the layers. So think about this right now as 5 times to the negative 5. Don't even worry about that crap in the middle, okay? It's junk. Just think about this as like stuff I have to worry about later. Well, you will have to worry about it. And by the way, this is going to be a long derivative, so start way over here. So think about when you just have 5 to the negative 5, you just bring down this negative 5, so you get negative 25. And now you get the crazy stuff, so you got to rewrite this whole part. And then you're kind of starting to freak out because you're going to have to deal with this later, but don't freak out. Okay. And then you reduce this by 1, so this becomes minus 6. Okay, now, don't freak out. We got to multiply this by the derivative of this guy. Okay, so where are we now? So now I have to multiply this by the derivative of all of this. So that's what's next. Okay, so that's fine. X squared, I can do that. That's just 2x. Don't start panicking. Think this is just blah to the power 3. Okay, so just think about it. You bring down the 3, you rewrite blah, and then you reduce this to 2. Okay, not so bad. Not so bad. But now we have to multiply by this, the derivative of what we just did. What we just took down to the power 2. So now we're in here. Okay, so just think about that as blah. Actually, no, this is just 3x, right? Oh, sorry, I forgot to close the bracket. Yeah, I need one more bracket closing. I knew something was wrong. Okay, so now the derivative of 3x is just 3 minus, okay, now don't freak out. We just have 4, so just think about this as 4 blah squared. So minus 4 blah squared. So we go minus 8, making sure, 1 minus x to the power 1, and then the derivative of in there is just minus 1, and then we're done. That is the derivative. We are not simplifying that. Don't worry. We are leaving it the way it is. But this whole long line is the derivative of that gross thing. Okay? I really encourage you to try that on your own now that I went through it and see what you can do. Otherwise, if you can't do it right now, just worry about more simple chain rule questions, and as you get better, you should be able to do this. All right, so before you come to class tomorrow, I'd like you to try these practice questions to kind of see if you can consolidate what you did. Part A using Leibniz notation, and part B is just like the example here and this example here. All right, phew, that's the chain rule. It's lots of work, but once you master it, it's a lot of fun too. Thanks for watching. Hope you learned lots.